Hello everyone, I am Mugdha. On behalf of Dr. Dhawan Academy of Geologists, I welcome you all to this first edition of our service on DDAG Talk Show on landmark developments in the field of engineering. Today we focus on Atal Tunnel. Built under the daunting Rohtang Pass, Atal Tunnel is a milestone in infrastructure development in India. The tunnel has been built by the Border Road Organization, that is BRO, a premier government organization that has been taming the mighty Himalaya. The tunnel being another feather in their cap. SMEC International Private Limited has been their detailed engineering consultant. To know more about geoengineering aspects of the Atal Tunnel, we have invited experts from SMEC Australia and SMEC India. Ms. Neeta Arora, a civil engineer, head of design center at SMEC Gurgaon. She has been actively involved in designing several major infrastructure projects in India and abroad. Hello, ma'am.
Hi.
Mr. Robert Goldsmith, a geologist, Chief Technical Principal Engineering Geology with SMEC Australia, based in Melbourne. Outside Australia projects, he has been involved in several hydropower projects in Asia and Africa. Hello, sir.
Hello there, Mughal.
Mr. Prashant Aggarwal, a civil engineer and senior general manager at SMEC. He has experience in all the aspects of project planning, design, and construction advisory services in several hydropower and tunnel projects. Hello, sir.
Hi, Mugdha.
Mr. Rajesh Arora, a civil engineer by profession, a senior tunnel expert and project manager at the Atal Tunnel for SMEC. Hello, sir.
Hi, good morning.
Last but not the least, we have Mr. Yogendra Deva from DDAG. Mr. Deva, a veteran of field engineering geology, is a formerly voluntarily retired director of Geological Survey of India and one of the senior most practicing engineering geologists in India. He is playing anchor's role in today's talk show. On behalf of DDAG, I welcome all the experts and request Mr. Deva to please steer the show.
Thank you, Mugdha. Thank you very much. That was a wonderful introduction of the program and our experts today. And if I may say that, so major underground structures in the Himalaya have always invited attention of the Indian geological and engineering fraternity. That way, the Rohtang Tunnel, named and commissioned as Atal Tunnel, is no different. Construction of a tunnel as long as 9 kilometers at a depth of about 2 kilometers through the lithotectonically complex Himalayan rock sequences is no mean business. We all know that. So we at the Academy are privileged to have on board the key members of the detailed design consultants who have made this gigantic project see the light of the day. So without wasting any more time on the formalities, let us hear the story of the Atal Tunnel from the team that wrote it. To begin with, I think it is better to have a look at what the tunnel is. So I can request, I think, Mr. Prashant Aggarwal to say something about the significance of the tunnel and its salient features.
Thanks, Mr. Deva. So it's a great to be with this show. This project, as you are aware of, this project, this tunnel is located in the northern part of India, in Himachal Pradesh. So basically, if you're aware of the terrain, so if you have to travel from Manali to Ladakh or Leh area, then you have to pass through the Rohtang Pass. So which is a higher peaks, and it remains snowbound for almost 5 to 6 months. So that ultimately leads to closer disconnection of that region with the remaining part of India for almost that regions. And it was a great problem with the habitation on that side for any medical emergencies or anything. And even it was not helping the tourism or the development of that part. So Government of India has thought of this tunnel way back in late 90s and early 2000 to have this proper connection which can be available throughout the year. So this tunnel connects the Manali to the Leh and Ladakh region. and it can be available throughout the year. And it is certainly a big development for the whole Lahore and Spiti region, and not only for the local, it's a important development from the strategic point of view for the Indian Army, because it connects the China and Pakistan with the remaining part. If we talk about the salient features, so this tunnel is more than 9 kilometers long. If we take the tunnel as well as the buildings and the avalanche galleries. So this tunnel has only 2 portals, and there are no edits in between. So the big task was excavating this 9 kilometer long tunnel with no access in between. So the whole tunnel is excavated from the 2 portal sites. And even above, after that, that north portal, which is on the Lahore Spiti Valley side, that remained normally cut off for 5-6 months. So the excavation was further more challenging, and major part of excavation was to be done from south portal, which was on Manali side, and the remaining portion can be done from was done from north portal side. Apart from the tunnel, we have the 2 portal buildings on both the portals, which houses all the electromechanical and ventilation and other equipments, and the control center for the whole tunnel. And on the south portal side, we have a big snow avalanche just outside the tunnel. So there is an avalanche gallery has also been proposed, so that that avalanche can pass through over that gallery. And apart from that, there are structures within the tunnel, like there are different niches to house the mechanical and other equipments, and the water caverns, etc. And the specialty is that it's being a single tunnel, there is no the other escape route. So escape route has been made down below the pavement. So there is an egress tunnel within the main tunnel itself, which comes out on the both portals, so that it can be used of any emergencies within the tunnel. So yeah, that's the broad features of the tunnel.
You're on silent.
Yeah, I think you are muted.
I'm sorry, I muted myself. I'm back to the audio. So I mean, thank you very much, Prashant, for this. But as you say that the portals are in on different sites, in Ladakh side, it's Manali side. So I understand that probably there is a lot of climate difference on these two sides. Can you throw some light on that? And in particular, like the elevations of the tunnel or elevations of the ground over the tunnel, and something like that.
Yeah. Both the portals have a significantly difference in the weather conditions. Like as you said, this south portal is on Manali side, and okay, you can access up to December, January. While in north portal, it's a very harsh climate conditions. So from November onwards, you don't find excess and a heavy snowfall conditions in the north portal side. The tunnel is almost around 3,000 meters elevation, but the south portal side it's a bit better climatic conditions, while the north portal, which is on Lahore and Spiti side, that remains inaccessible throughout the year. So it's a very harsh climatic conditions on the north portal side.
Thank you once again. And I think before proceed with the tunnel design, engineering, and other side things, I think it is better first to know about the ground conditions, the ground appreciation, I mean the geology. So I will request Robert to please enlighten us on that. We hear that he has done lots of work in that area, and there have been constraints, lots of constraints in the conventional investigation and exploration approaches. And in particularly, I would ask him to give something more about the Sirinala problem, Sirinala Fault problem, that I think has been one of the biggest challenges in the construction of the tunnel. So Robert, over to you.
Thanks, Mr. Deva. Yes, I was involved with the project from just after the design work was awarded to SMEC back in 2006, 2007. There had already been some drilling investigations and some basic work done, which we inherited that information. But a lot of the challenges due to both climate and elevation, that further drilling was not possible. I mean, the extreme distances to drill 200 to 400 meters into the ground, but that was overcome partly by doing geological mapping, and there was a lot of very good rock exposure. We were able to identify where the main rock types were. There's quite a complex metamorphic materials, naming a few of the rocks: schist, gneiss, phyllite, and quartzite, and they each have their own inherent difficulties. Even though quartzite is a hard rock, it does get very fractured, and it can cause lots of challenges for inflow of water and so on. And well, on the other extreme, we had some of the rocks like the gneiss, which are extremely hard. So there was the potential for rock burst in the high overburden pressures impacting the high strength rock. And particularly at the northern end was much harder rock than at the southern end. The portals were already set and fixed. We adjusted them very slightly. On the Manali side, there was a lot of colluvium, but there was the portal was actually cut well into the rock. There might have been some adjustments to getting it in the portal area, but we soon went into fairly good rock. However, about 1.5 kilometres along from the south portal, there's a fault called the Sirinala Fault. It was oblique to the most of the Himalayan faults sort of travel along the line of the ridges, you know, north, east, west approximately, but this was sort of cutting an angle northeast to southwest. And this was due to some major tectonic events since the emplacement of these rocks in the Himalayas. And but the rock over several hundred meters, it became. I wasn't there during the construction, but I was able to track what happened. The full face of the 10-meter diameter tunnel was ended up being very sandy material. It was, and a lot of flowing material. So there was very great difficulties. It was probably good that it wasn't a tunnel boring machine in this material, because we might have had a tunnel boring machine stuck. But they got through with the range of tunneling methods that I don't know the details, but it took quite a few years to get through this particular zone. But they did get through, and but the other tunneling work was I understand achieved quite well. But going back to the geological mapping work, we actually had quite an interesting team come into that site. Apart from our fellow Indian geologists and myself, we brought a few people internationally, including an experienced geologist that I had worked in Papua New Guinea, the South Pacific nation of Papua New Guinea. And he was probably the first Papua New Guinean to come and work in the Himalayas. And he picked up the Hindi language better than I could, because he was actually conversing, and sometimes they wondered which part of India he came from. So he did a brilliant job in mapping all those complex areas, even up in the narrow gorge of the Sirinala Fault. So I don't think there's anything more I can add at this stage, apart from the fact that the north portal was covered in very deep snow in the wintertime, and so you just couldn't get in there. I mean, access roads were another issue, because you had to get across quite a significant river on the north side. And also there was mention of snow and ice avalanches, and that the access road from the south. We also had to cross a few of those, and so there was a special design and monitoring had to be done in those areas. So anyway, back to you.
Thank you, Robert. I mean, that's a good information.
Unless there's any other questions.
I just had one query, because I understand that probably the exploration was not possible. I mean, the cover was too much, maximum cover was too much. I think in the range of 1900 or so. So as you have also said that you depended more on geological mapping. I'm also a firm believer that geological mapping gives you all the information, and exploration just confirms it mainly. But in this particular case, I know that along the alignment, the mapping would not have been possible, not even close to it. So what were your target areas for the geological mapping? I mean, you went along the existing footpaths and roads closest to the tunnel alignment, or how did you carry out that work and then projected that?
Well, okay, yes, very good question. There were, I guess, 3 or 4 different ways of assessing that. There were existing tracks from the south side into the Sirinala. There was traverses were done and structural interpretations done there. We also, the Rotang Pass Road was looked at because a lot of the structure was cutting across, so we could do some correlations from there. On the North Portal was a very long, steep slope with a lot of loose rock scree. And so there was a lot of safety issues with getting into there, but there were some tributary streams nearby. We also had a helicopter trip, and were able to do some monitoring or picking up some information that we couldn't see from the ground. And there was also satellite imagery was used to pick up the major structures. So combining all that, we were able to produce what we thought was a reasonable geological profile. We had test data from the early drilling, so we could assess a lot of very generally interpreted rock mechanical conditions. And of course, the in situ stress was assessed from more regional stress map, and there was no specific stress, but and groundwater was known from some of the drill holes, so we were able to make some a best estimate profile along the tunnel with quite a considerable amount of material to enable the about 7 different support classes to be assigned along the tunnel alignment.
Thank you. And the one last query, a small one. As you said that the North Coastal was in very steep slopes, and
Yes.
Otherwise accessibility was not there. So did you think about photogrammetry or terrain photography like that, things to study and get some data from there? Or simple photographs were taken and analyzed?
Back in those days, you could only do the photogrammetry from the ground. We didn't have drones and all these wonderful things we have now. So we did rely on some satellite imagery for that, and there was some reasonable topographic mapping done, but still was very general. Photogrammetry was not relied on because there were no really clear rock faces. There was enough that you could actually go and map particular outcrops and pick yourself by GPS and plot those on. But I guess these days we might have had more things at hand to help us, which and that really has transformed the way things are done now in the last 5 or 10 years.
Mr. Robert, I should tell you one thing. While I was at site for 10 years, I should appreciate your one of the good effort, because while in the tunnel it's okay. We have a less opportunity that we know there was a groundwater in the Sirinala. But of course, I don't think so we can somehow tell what will be the influence of groundwater during execution. I don't think so this is possible today and tomorrow also. And one thing which I would like to appreciate is, while we were looking to do some alteration in the south portal control room building, but we could not do because even shifting building by 1 meter, we were entering to the loose material. So that is what during your investigation you have so well located the south portal ventilation building that it was the last column of the building was coming exactly on the rock, not on the loose material. So I should appreciate your this evaluation and investigation during that time in 2008.
Now I recall there was an alternative portal considered by our design engineers, which would have gone obliquely into the colluvial materials, and so they would have had to do canopy tubular pipe support, but that was avoided by one of the problems was that the road went along the valley side and had to turn a steep angle to go into the tunnel. So, but going into the rock was, and then that way you could get into the rock. But I think the portal facilities had to be built out so that could be. I think that was a lot of because a lot of tunnel planning is surface works as well. Because you have to bring in all the equipment and all the water and the power and the ventilation and fuel. That all has to be put in a stable place as well to support the underground works.
Thank you. And I mean, in this connection, I had one query from Neeta ma'am. Because we know that we face lots of serious issues by for getting the techno-economic clearances from the government. So in this particular case, when we were lacking in exploration part, particularly, and we were depending more on engineering geological mapping. So I presume that that must have been a big hurdle in getting the clearances from the concerned departments. I'm not sure what kind of for such a project. This is not a hydropower project, and certainly you need some clearances. And how did you manage that? How did you convince them this is the best you can do? Ma'am, please.
Okay, I think for this particular project, RISE was involved in making the DPR. That initial phase of the very initial planning was done by RISE. When SMEC came into into the project, it was mainly for detailed design, and when it was ready for construction, this being a very strategic tunnel, being a very important tunnel. So Rajesh can throw better light on this. In fact, I think our role was more on the engineering front, clearances, etc. I think BRO managed them well. Rajesh, anything you have to comment on the clearances aspect?
Yeah, I can just.
Rajesh, I mean, Prashant, in the meantime, by the time Rajesh says something, if you can fish out some basic, I mean, drawings and some photographs, giving us an idea about the project. So that would be great. From your record.
Okay, let me see. I will share some photographs.
So after now let's go to Rajesh. Thank you, Rajesh. Please. Yes, Rajesh, you can go ahead.
Yeah, okay, fine. Okay. Actually, in this project, we had what we can as a good thing that there was no population on the alignment, there was no village, and there was no very thick forest involved also. And also, since there was no village or population, so there was no major this thing that we can lower the groundwater table also. We had a flexibility that groundwater table was not majorly discussed. We could even lower the groundwater table, and that's the reason we designed this as a drain tunnel. So getting the permissions for execution of the project was not I should say, to my experience and knowledge, was not a very big challenge for this Atal Tunnel. Had there been any, likewise we say, national parks or sanctuary area wherein we had a prohibition of this drilling and blast, so we could, and it was mandatory to go with the tunnel boring machines in that case. So there was no sanctuary park. So of course we could choose the construction method as required, and lowering of groundwater table as in case of metro tunnels where if you lower the groundwater table, we have a consolidation of the area which causes a sinking of the structures also on the alignment. So this issue was also not there because it was Himalayas and there was no construction on the alignment. So this also was a major relief to us that we could choose drill and blast because of absence of any sanctuary area or national park, and groundwater table was also not an issue. So there was not a big task for getting the clearances from the various departments. And also it was a project which was related to the defense for the strategic point of view. So everyone was cooperating in that way.
Yeah, we understand. Thank you, Rajesh. Now, Neeta ma'am, I think now is the time for getting into the most challenging part, that is the detailed engineering and the design. And I know that probably this egress was an innovation in design for this tunnel. Single lane tunnel was made. So we are all ears. Let's have some details about the design, ma'am. Thank you.
Yeah, thank you, Dev sir. Actually, Atal Tunnel, as we all know, is a 9-kilometer long tunnel connecting the Manali region to the Lahore and Spiti areas. The elevation difference between the two portals is not significant. I mean, it is of the order of 3060 to 3071. So, but as Prashant had mentioned earlier, the climatic and the approachability conditions were better on the Manali side, and therefore, we could there were more tunnel, excavation or more work took place from the Manali side portal. Coming over to the design aspect, see, in a highway tunnel, in a long highway tunnel, ventilation design, fire safety, and evacuation in case of an issue of fire, etc., forms a major aspect in configuration, in designing the configuration of the tunnel. So, to my mind, at least 30 to 40% of the civil cost of the tunnel goes for providing an evacuation system in case of a fire or an emergency. So in case of highway tunnels, you definitely need to have an egress. Long highway tunnels, we all know the codal stipulations, it's more than 1.5 kilometers. So this being a 9-kilometer long stretch with accessibility only from two portals, there is no intermediate shaft, there is no intermediate edit in this tunnel. So egress design definitely was a challenge in this case. Recently, we are seeing that there's a concept of providing one main tunnel and then a parallel egress tunnel in case of relatively long highway tunnels. But in Rohtang tunnel, the real beauty is that the egress has been located just below the pavement, which is a very innovative design. Now, some people may have pros and cons for this design. Because it makes the tunnel diameter, vertically, the clearance becomes larger. But to my mind, providing a parallel tunnel only for egress, which is being done in some of the projects, recent projects, could have its pros and cons. But we will focus on on Rohtang. How providing a egress below the pavement was a cost-effective solution. In Rohtang, we have faced very challenging geology. We all know about the Sirinala and then the other geological aspects. So basically, it was a modified horseshoe in case of a good geological condition. But when it came to poor geological condition, we all know that a circular shape of the tunnel is much better. Now, if you are giving us, a near circular shape of the tunnel, then the lower part of the tunnel becomes, that space becomes, kind of not very properly utilized. It can be used for drainage, it can be used for passing the cable ducts, etc. But in Rohtang, we have used that space, which is in the lower part, to form an egress passage. So I think it was a good solution. We did not have to go for a expensive solution in the form of a parallel egress tunnel. which was probably an option available to the designers. Of course, there are connection tunnels or passages from the main pavement to the bottom egress. But to my mind, that space below the tunnel, because significant portion of the tunnel would have been otherwise anyway, because of structural reasons, near circular, has been very gainfully utilized. So the egress size is 3.6 meters by 2.1 meters, and that is big enough to pass a small vehicle as well, as some of us might have seen, or during the inauguration when the Prime Minister even entered that egress passage. So I think that's the real speciality of this tunnel.
Thank you, ma'am. I believe that there was another challenge, that was the atmospheric pressure difference at the two portals. So I think did you require any special arrangement for that, tackling that?
Okay, Prashant, you've been dealing with the MEP. Can you answer this one?
Yeah, yes, Deva, this was a big issue because of the atmospheric pressure difference between the two portals. So the ventilation system was designed according to it, and we can tell you there were significance of that, and even the capacity of the ventilation fans were assessed based on that, so that we can utilize the flow conditions when the tunnel is in operation, and even during the emergency cases, all the smoke, etc., can be taken out immediately. So the ventilation system has taken care of it while designing it.
Okay, thank you. And now I have before we go into the construction methodology, I think which Rajesh can answer, I think. I was just wondering, but at about 9-kilometer length or something like that, with no scope for any edit or shaft for construction, TBM use of TBM must have been a consideration at some stage. And because this was the right length, in fact, you put two TBMs on the two ends, do it, and bury them in the mountain afterwards. So why was TBM not preferred at this site?
All right, I'm glad that TBM was not used in this project because the TBM technology that we had 10 years ago, and the kind of geological conditions that we met in the tunnel, I think would have been really challenging if a TBM was deployed on this tunnel. Of course, there has been a success story in the Himalayas using a TBM, a long TBM, but I think Rohtang, the geological conditions and the water ingress, they're now known to everyone. And only what I can say is that the designers at that time, I think they took a very wise decision of not deploying TBM on this particular project, because one, it would have been super expensive, much maybe the cost would have been more than double. Number one, in fact, the initial cost itself would have been much higher. Time-wise, the TBM technology, I'm not sure at that time, 10 years ago, whether it was to that level to have negotiated the Seri nalla stuff. And we all know when TBM gets stuck, then the kind of challenges we face in, retrieving the TBM, etc. So that's what I have to say on the TBM part.
That's very convincing, no doubt. And now I think we should come over to a very special part, that is the construction methodology, excavation methodology, and support system. So I don't know whether, ma'am, you will answer that or Rajesh will do it.
I think Rajesh, please take this on.
Okay. Actually, when we were discussing about TBM, what said by Neeta madam, I think so that was the first win. And to put a stamp that project will be completed, and SMEC said that no go, that we can go with TBM. As you said, Mr. Deva, that the length was very much ideal for choosing the TBM 9 kilometers. We could go on with the 1 TBM also from South Portal. But the thing is, we had a deformation of 1.2 meters in the very good rock also because of the high overburden. And in the fault zone also in the Sirinala, this fault zone length was 500 meters. And I think so, had TBM would have been chosen for this project, I think so, we would not have been discussing the innovation in this year. This was the in 2008 when SMEC said that we will go with drill and blast. I think so. We put a stamp that we will complete the project somehow. As I said you earlier that because there was no issue of the mandatory requirement for the government that this alignment was not having any national park or sanctuary area. So we had a flexibility to choose drill and blast or TBM. Very sensible and accurate decision from SMEC in 2008 and or 7 that TBM cannot go in this Atal Tunnel. So that's why we came into the drill and blast. And drill and blast, typically, it is well known to all. And of course, you are very experienced also that it constitutes of drilling, charging, blasting, and then mucking and putting the rock support and then go ahead. This is okay for the ideal conditions. But as said by Mr. Robert also that we had a heterogeneous ground conditions. I will tell you my experience in the full perimeter also. Let's say we have a perimeter of 24 meters in the top heading. The height of top heading was chosen as 7 meters depending upon the equipments which contractor was intending to use. And we used 3-arm automatic boomer for the top heading. And in the one perimeter of 24 meters, we had a different ground conditions on left side, different ground conditions on the right side. And you will not be surprised to know that on the left hand side, we use the self-drilling rock bolts, which requires very loose material. And on the right side, we use the Swellex bolt, which is a friction bolt. So you can somehow imagine the type of rock on left and right. So it was a very challenging, and of course then we had for the support system we had a Q classification or the deformation based ground behavior based rock support evaluations. So Q system is very simple to use that we can calculate the Q value and put the rock support, but it certainly doesn't work because we work out the Q value based upon what we see from the face. But what we get squeezing is from the outside the face, which we cannot see. So this we can see from the deformation values, and based upon that deformation values, we have to install the rock support. And also, I can tell you, I maybe later what we can share some pics. In the North Portal, it was a migmatite rock, very competent rock, but it was 2 kilometers. Still, we had a collapse. We had a deformation of 1.2 meters, which made the tunnel collapse for, let's say, 60 meters. So I think so in migmatite, collapse is not very usual because the overburden was very high. So this was, and we had a shearing failure in the North Portal. This means if you see from the clockwise, at 1 o'clock to 3 o'clock, it was failing at 1 to 3, which need a very stiff support. And on the other side, it was okay to go with the normal, simple, good spacing of the rock bolts also. So this was very challenging in terms of execution, in terms of design, and of course the Sirinala also. I will tell you one thing of Sirinala. We had a stoppage of in total, Sirinala length was 500 meters, and it was done in 50 months. So let's say 10 meters average progress per month. But there were 9 to 10 months when there was no stoppage at all. It was standstill, 0 meters for 9 to 10 months. But still, I believe we had a lot of brainstorming in that discussion. Every day we were discussing how to proceed, what is the solution ahead, how we can have a safety also. In safety also, I will tell you one thing, that there was no fatality in the inside the tunnel. Even after having 1,000 cubic meters muck flow also with lot of water, so it was so well constructed. Yes, I don't say that even the estimated time, we took 10 years to complete this tunnel, but I think so the estimation was a bit on the very lower side, that it will be completed in 5 years, because there was many challenges: climatical challenge, geological challenge, fault zone, high overburden, closing of one portal for 6 months. So it was, I think so, well constructed tunnel in a good time. I believe so.
And one more thing to add on is that we in Rohtang we talk much about Sirinala, but that is not the only stretch of problem in this tunnel. There are many stretches, even where the deformations were not stabilized even for years. So those were also very problematic zone, and many times the corrections are done in the sections. Rock supports are increased to stabilize. Even I think in couple of meters section still the deformations are going on, still going on.
Okay, so I understand that this flowing ground condition, for a mind-boggling width of 500 meter, quite a long. So this was the only problem, flowing ground condition, and no other shear zones or faults along the tunnel posed any such problem. Not even
No,
on
as said by Mr. Prashant also, and I said you before that, apart from the shear zone of fault zone of Sirinala, we had in North Portal, it was a migmatite rock, very hard, good rock with the thick formations also. There also we had a collapse of the tunnel because the overburden was too high of 2 kilometers. This brought, I'm telling, which had a major problem. We had we have many minor problem which we cannot discuss now, but two major problem. In the good rock also, we had a collapse of 60 meters for a length of 16 meters.
Thank you very much. I have just, I think for wrapping up, I have just a small, 2 or 3 small questions. But before that, I think if Prashant can show us some visuals of the project, we would love to have that.
Okay, yeah, sure.
We have some, yeah, you can share the screen.
Okay. So just to start with the this is the alignment of the tunnel on the Google map, just to give an idea of how the overall topography is for the tunnel. And so this you can see this was the earlier alignment, and now this tunnel is crossing through, giving the shortest possible route. And this, if you can see the L section, where you can see how the overburden or the rock cover is varying along the tunnel. So it goes up to the almost 2 kilometer, and then it comes down. So you can see a higher cover on the North Portal side, while in this area we have the Sirinala Fault zone. If we talk about the section which we were talking about a lot, how the Egress Tunnel is planned in this tunnel. So you can see that this topmost portion is being used for the ventilation system. So there is a slab which segregate the pavement or the traffic area with the ventilation duct. So this is the total tunnel is in 3 parts. So the topmost is for the ventilation duct, and the in center, the middle portion is for the actual traffic movement, and the down below we have this egress passage for this emergency evacuation. And on the 2 sides you can see all these cable system and the drainage pipe arrangement, which brings out all the seepage, water, etc. outside the tunnel. Just to show you about a couple of photographs.
Sirinala Fault flowing ground condition in tunnel.
Yeah, let me see for the photographs for the Sirinala.
That is the most talked about challenge.
Okay. So this you can see, this was the Sirinala stretch, where the different type of options have been explored during the excavation. So you can see these are the actions taken. So this was the total stretch for the Sirinala. This was the during the first phase, and when you can see this all this flowing ground condition, then you can see that it was excavated through multi-drifting. So these are the stage-wise excavation done in the Sirinala stretch. I'm not able to find one video. There was a video which can show how much amount of seepage water was coming in this stretch. It was like raining inside the tunnel. I was just trying to locate that video. So you can see this. This was the condition of Sirinala. And this was okay during excavation, but now we can see a couple of good photographs after the excavation.
Wow, that's beautiful.
Just let me open it in this so that I can quickly pass through. Yeah, so this is you can see now this is the finished section.
While driving, one will never know what happened here.
Yeah, that's what exactly I was coming to say. When now we are driving, everybody will just forget what has happened in last 10 years.
Yeah.
And this is you can see how the south portal looks like.
Beautiful.
Mr. Deva, the only one thing now, if I remember my time when we were supposed to go from Manali to North Portal to have a look about the work. Initially, it was taking around 12 hours, and now it's taking 12 minutes. So scale has changed from minutes to hour. That's it. So we have lot of saving in fuel, lot of saving in health, because getting stuck in traffic jam is of course not so easy. It takes 12 minutes to come from North Portal to South Portal, which is 12 hours before.
And this you can see from the North Portal side how once you are coming out of the tunnel, how because how this zigzag is there, and then you reach to this bridge to cross the Chandra River. So there was a lot of planning which has gone in planning of this ventilation building.
So this is Chandra River.
Yeah.
One of the two rivers, Chandra and Bhaga, who make Chenab River.
Yeah. Yes, you are right. Yeah.
Lovely. So good photograph.
So this you can see the bird's eye view of the North Portal.
Thank you very much. And before we wrap up today's discussion, I had just some small queries from, I think Rajesh can answer that. One was the contractor. Who were the contractors and what was your experience with them? They must have done a very good job here on this tunnel, so that it has seen the light of the day. And secondly, what was the cost of the project? Time, I think you say about 10 years, total construction time.
Yeah, the first blast was in August 2010. That was the first blast.
Okay.
And we completed in 2020 October. So
yeah.
it's 10 years, yeah.
I think it's quite reasonable time for such a tunnel. And how about contractors?
It was a joint venture of Strawback, which is a Austrian contractor, a European contractor, and Afcons, which is a Shapoorji Pallonji group. So Strawback, I think, so is a very, in my opinion, is a very sensible contractor, very experienced contractor, and they know their subject also. That's the reason they got this tunnel. And if we say about the Afcons, I believe in the current scenario, the Afcon is doing good jobs. Good job. Yes, they have done a very sensible work. That's appreciable.
And finally,
for electromechanical, the contractor is Savronic, the Turkish firm.
Okay. And finally, the cost in terms of rupees per kilometer in crores, and how does it compare with the cost of other highway tunnels of the same size? If madam can answer that, I don't know.
Total cost per kilometer would work out to somewhere around 3,000 CR is the total cost to my understanding. So 333 CR per kilometer for a 2-lane tunnel with egress is the cost. We also looked at recently cost of some tunneling with a separate egress in J&K or in other parts of India. So cost in the present scenario works out to somewhere around 350 CR to 375 CR per kilometer. That's what we worked out with a separate egress. So yeah, actually, costing has been, if you do a cost analysis, most of your SORs, etc., or your manuals in such high altitude tunneling or working in such high altitudes and with such restricted available time for working, especially on the North Portal side, we had only 6 months for working. South Portal, of course, the available duration for working was longer. So there were all these factors which compounded. But I think this is the cost that is reasonable and is working out in such climatic conditions.
And even if we talk about Rohtang, means the cost would have been lesser if this we haven't encountered Sirinala. So because of the time overrun, ultimately cost has also gone up. Otherwise, the cost would have been much reasonable or much lower side for Rohtang.
So thank you very much. I mean, I don't have words to thank you, basically. And my huge compliments to the SMEC team for doing this wonderful job and giving us the first, I think, Trans-Pass highway. The next one, highway tunnel. And the next one is coming, that Zojila. That will be no less challenging job, considering that the tunnel length is 14 kilometers. So maybe we get sometime to discuss that, if that suits everybody. And let's see how it fares. So thank you very much. And I now hand you over to Mugdha for the closing remarks. And if she has any query of her own on these things. Thank you, Mugdha. Thank you.
Thank you so much. I thank all the experts for sparing their valuable time. At DDAG, we'll be coming up with many more talk shows on current affairs in the field of geoengineering, like the one we just had on prestigious Atal Tunnel. So stay tuned and take care. Keep up social distancing. Namaskar. Thank you.